Good morning. I'm Travis Gockel, and I work for SolidFire as a C++ pirate. That is my official job title. It actually says that in the org chart, which is pretty cool. And today I'm going to talk about completions, which are our internal implementation of futures. They're an alternative to futures, and I feel they work better. I only realized yesterday that I had a half an hour to talk instead of an hour, so the last half of this presentation is in the extra. I'll be posting the slides somewhere, so I'm not going to get to any of the extra parts. So first things first, who is SolidFire? What we do, we are a distributed all-flash block storage vendor. And what that means is we take a bunch of computers, we network them together, and then we present them to users as a bunch of hard drives. People connect to us over iSCSI, and we're kind of a high-performance solution. Because we're an all-SSD vendor, you have to be. Because we're a storage vendor, things like data loss and unavailability are 100% unacceptable for our users. Our users are cloud service providers. If they have downtime, that costs them a lot of money. So even in the cases where, say, a network card fails or a hard drive fails or whatever, we have to keep running, no matter what. We deploy as an appliance, and what that means is there's no administrator that comes along and babies the cluster as it goes through time. It has to be a self-maintaining entity. And we deploy in environments we don't control. So we don't have control of the power, we don't have control of the network, we don't actually have control of the heat, and we have to make our software and our hardware respond to this in really good ways. I guess the best ways that we can. We have a pretty small engineering team, at least in my opinion. We have 40 C++ developers, or slightly less than. So that means the efficiency of our developers is really critical. And we're also hiring, and what that means is when new developers come on board, we have to make sure that they can come up to speed pretty quickly. So the language we use can't be completely foreign to them. So here's just kind of an example of one of the algorithms we look at. This is how we do reads. So a request for a volume, an offset, and a certain amount of data comes in. We hit the metadata, we figure out some internal IDs for that. Sometimes that data is in the cache and then we can serve that immediately. Sometimes it isn't. And when it isn't, which is, I guess, most of the time, we have to fetch the associated chunks over the network. And then in the end, we take all this data, we combine it back together, respond to the user. So there's a lot of algorithms in our system that are fan out, scatter, gather, collect, return. So in this case, for reads, the user visible latency is the worst case of our responders. So what that means is we're extremely sensitive to latency. So whenever I talk about, oh, that's slow, I typically mean in the case of latency, not throughput. All right, so since I'm presenting an alternative to future, I feel like I have to justify why the original future is not good enough for us. So first things first, what is the goal of future? In reality, the future is a mechanism for communicating some sort of a provider, which is a promise, to some sort of a receiver. So it's a very low-level construct that says, okay, I provide you values that you shall receive later, and I receive them somewhere else. And in reality, this is supposed to make concurrent programming easier to deal with. So here's kind of the important functions that are part of future. The first and most important one is get. And what get does is, if the future has a value, it returns you the value, or it throws an exception. If it doesn't have a value yet, then it blocks until you actually get the value. There's valid to check for validity. There's wait to wait for it to actually be complete. Then there's the wait for, wait until. Those don't really matter. The last and most interesting one is probably share, which allows you to do something and then fan out. So a regular future is a one-time use thing. What a shared future is, it allows you to have n amount of receivers from a particular future. So how do I use this? I'll go through the very classic example of I want to read multiple things. So here I want to read location X and location Y. So I use async to start off a read of X, and then I read Y on my own thread. And then, of course, at the end, I tell my first future I want to get, so block until it's done, and then take Z2, and then kind of combine them into one thing. The problem with this is it's really only sort of asynchronous. So the issue is, if you're doing, say, hundreds of thousands of reads per second, then blocking a thread to wait on something as simple and fundamental as an I/O is absolutely preposterous. So futures don't really work for this use case. And when you're talking about a network storage solution, the majority of your operations turn out to be I/O type things. So really, what I think is wrong with future is that get and wait are actually the only two ways currently to interact with them. And really, these two functions should never be used by anyone ever, except for unit tests. So, then is coming to us at some point in the not too distant future, hopefully. And what then does is it provides you an ability to chain the next step of an operation for a future. So I take then and I say, hey, I'm going to give you this function. So here I'm taking x, which takes in, it's going to call thing, and return me an integer later. And then I'm going to say x.then, take this future, and return to you the cast it to a double, which isn't a very interesting operation, but it's an operation. So what happens inside of this lambda expression is this future is guaranteed not to block. So when I say f.get, I know, because I'm called through the context of a then, that this will never, ever block, which is kind of neat. But I think that's pretty awkward. And the reason why that's awkward is when we talk about aggregation. So imagine I have a vector of future integers called all tasks. And the proposal that says then has this other function, which is nice, called winAll. And the idea behind winAll is, well, I am given a future of the things that I give you, and I'm going to move those things over, and by the time all of those things are done, I'm going to be given back a vector of my future integers where I can call get on them, and none of them will block ever, which is very cool. The problem is, future is a multi-threaded construct. And the problem is, it has to deal with locking. So while I know, and the standards committee knows, that future.get will not block in the context of then, the compiler does not know that. So it means it can't optimize it. It means it has to take a lock. And if you really want to check me on this, add up the values in a vector of integers, and also compare that to the time it takes to add a vector of future integers. It's just slower. Another problem I have is somewhat philosophical. So in theory, these two pieces of code kind of do the same thing. So the one on the left side kind of looks like an insane person wrote it. You look through, we're catching everything just to rethrow it, and we're not doing anything. Now, if you looked at these two pieces of code, obviously the one on the right is the preferred modern C++ approach to these sort of things. And really, it's the good C++ approach for forever. But I would argue that the chaining of then operations is the same as the code on the left. Almost, except we're doing it through futures. So if you look through thens, we're repeatedly getting the next step of this operation. And if my first step of this operation through, then I'm repeatedly rethrowing an exception throughout my entire chain. And if my chain is significantly long, then I'm wasting a lot of time throwing and rethrowing the same exception over and over and over again, when in reality, had I written that code in a synchronous manner, it would have been a lot faster. All right, so I would argue that the real problem with future is that it's trying to combine two ideas. There's the asynchronous communication aspect, and then there's the reporting of errors. So one could argue that an error is also a type of value, but the way we deal with them is quite different. So there's this convenient mechanism that someone has proposed called expected, which allows you to take an exception and kind of act like it's a value. So if you've ever worked with optional, an optional can have a value or it can have none, and you can do stuff with it. An expected can either have a value or it can have an exception. And very similar to the way future works, get will either return you a value or it will throw the exception. There's some debate on exactly what the semantics there should be, but for now, I'm going to treat it as if it works that way. And then there's status, which returns a Boolean, true if it has a value, false if it has an exception. And then there are these two other functions called map and catch error. which are best demonstrated through example. So I first call this function foo, and it's going to return to me an expected integer. And at this point, I don't know, nor do I care, if that was completed in exception or completed in value. So the next step, I'm going to say x.map. And in this case, if x was completed with a successful value, then I will call the lambda expression. If x was completed with an exception, then my expected double will just take that exception and kind of move it over. Catch error has the exact opposite semantics. So catch error says, hey, if you have a value, I'm just going to return you that same value. And if you have an exception, then I'm going to apply some transformation on it. And you can do all sorts of things. In this case, I'm just saying, you know what, if there's an exception of any kind, just make that value 0. Then later, I'm going to cast them both to a string and then get my value and print it out to cout. All right. So now that I've covered all the bases, I can finally talk about what a completion is. So completion is a class that kind of looks like a weird amalgamation of the expected and future. So probably there aren't a lot of interesting functions on here if you already kind of assume what map and catch error do. The only weird one here, I guess there are a couple weird ones. One is onComplete, which doesn't return anything, so I'll cover what exactly that means. And the other one is disable, and I'll talk about that later. So the things that you might notice are missing are get and wait. And of course, the reason they're not included is done on purpose. You should never call get and wait. But we can include them if we want to be compatible with std_future, and I'll actually show that in a bit. Another thing we lack is overloads for the reference type and void. So if you look at the implementation of future, the standard says you must overload it for reference types and void. Well, it turns out if you just let your expected implementation deal with that, then it's not a big deal. You don't have to kind of do all this weird overloading or implement your code twice or do anything funny. You just get to use the expected. All right, so to jump pretty quickly into the implementation, we have this thing called a completion data. And if you know how futures are implemented, they're done basically via the same way, where you've got kind of this shared piece of data that both your promise and your future have references to. In our case, the probably most interesting part is this spin mutex at the top. So instead of having a regular mutex, since our quantum of work, since we know that get and wait are never used, our quantum of work is very small. So it's kind of a get in, make your changes really fast, and get out as fast as possible. So it turns out that a spin mutex is way faster for this sort of thing, because you're not doing that many operations in here. The status is for status tracking. There's an optional value because you start off without one. And then, of course, there's a callback, which we'll get to later. We only support move semantics on callbacks, which is the nice thing about being a modern shop. And then there's this last bit called reference tracking data, which is essentially an intrusive shared pointer. All right, so the completion status kind of goes through a number of these state transitions. You start off with no value. So you start off with no value, and if you disable it, then you go into the disabled state, as you might expect. If a promise is destroyed without setting a value, your completion is broken. I'll get into what exactly that means in a bit. If you do a chaining operation like map or catch exception, or then or on complete, then you go into the has callback state. If you set a value before you set a callback, then you have a value. And then going from has value to complete or has callback to complete is kind of the opposite of how you go from no value to either has callback or has value. So there's kind of a simple state diagram for the things that we can go through. Oh, and you can also go from has callback to broken. Worry about that later. So then is kind of the most important function that we kind of think of. It actually is mostly equivalent to std_future then, except instead of like std_future where you pass in a future, we give you an expected t. The semantics are exactly identical, except it's ridiculously faster. And by ridiculously faster, I mean we don't have to take a lock, we just forward it directly to you. Because, well, at this point, we can guarantee through the type system, not through some weird semantics, that you will never have any contention on this expected value. So if you have a value, so if you call then and you have a value, we will call func immediately. If there is no value, we store func for some later use. In all other cases, there's an error. And depending on how you've configured it, it can either be a logic error or it can just crash immediately. So another kind of sibling function to then is onComplete. And onComplete is actually how then is implemented, except the key to onComplete is it does not return a value. So if you look at the flow of data, the last step in your process, you probably don't actually want to take a value back. So the last step of your process, so if you think about thens and you're chaining a bunch of operations together, the last one is where you are no longer chaining anything. So this kind of allows us to do fire and forget. So in a lot of cases, we're firing and forgetting. And we say, okay, when you're done, just don't allocate another completion data for me. So this saves us a lot of small block allocations, which is nice. So there's also map, which is very, very similar to then, except it's only called in the cases where there is a failure. So this actually improves speed a ridiculous amount. So it's very easy to check this by always throwing inside of your then. So imagine if you have a map function that is implemented simply in terms of then, and you always throw, this speeds up the system. And unfortunately, I can't give you good benchmarks because any trivial benchmark is basically me pulling the wool over your eyes, so I'm just not going to do that. So catch error has the exact opposite semantics of of map. So we can also implement get, and we implement get by saying, okay, we're going to just make a promise of an expected t, and we're going to set onComplete to set our value. And we're going to move our expected into that, and in the end, we're going to return promises futures.get.get. So this is really awkward looking, but what that's doing is we're grabbing the future, we're grabbing its expected t, and then we're grabbing the expected t's get to give our completion get the same semantics as future get. And I realize that I used to say get a lot, but that's okay. The key here is that we only incur the slow mutex call for the cases that somebody actually asks for this slow get call, which is very powerful. We can actually do the same thing with wait, except we have to do some internal tricks because just like a future, a completion can only be fired once. So we have to make sure that if you implement wait, we don't actually destroy your future. All right, so the other side of things, so how do we actually provide values? Just like with a regular promise, we use completion promise. And what this does is it gives you the delivery of values to our completion. Okay, great. It shares the completion data just like a standard future implementation. So it has one function that is different from standard future, and of course the title went off the screen. This function called complete, where you give it an expected value, and it simply checks, hey, if you have a callback, please call that callback immediately. If there is no value, store the value for later retrieval. If the completion status says it is disabled, just do nothing. So drop that on the floor, don't call anything, call it a day. All other cases are an error of some sort. We can also be compatible with the standard promise. So by saying set value, we just call complete with make expected. And when we set an exception, we complete with make unexpected. So kind of gives the same semantics and makes completion promise a drop-in replacement for STD promise. So as a refresher on the transitions, we're going from no value to either disabled. You can break if you destroy your promise. You can set your callback on the next chain. or you can set values and give it a value for later retrieval. Cool. All right, so let's talk about edge cases. So first things first, broken promises. These are kind of a big deal. So when your completion promise is destroyed without setting a value, what should you do? And there are a few options. One, of course, is to do absolutely nothing. Simply continue on your merry way and cause a deadlock somewhere else. Because if somebody is depending on your future somehow getting completed, well, either we're going to cause a deadlock somewhere, or we're just going to have this task that's kind of in the ether of stuff that, well, may or may not ever get completed. So somebody asked for something, we've abandoned that task, the completion never gets delivered. Maybe that's okay. You're probably going to memory leak. So you generally don't want to do this. In our case, we do not allow this state. But originally, we had kind of a configuration option to allow you to do absolutely nothing on broken promises. Turned out wasn't a good idea. Another option would be to deliver an exception, say a broken promise exception, to that completion when you destroy your promise. Of course, the issue with this is when we deliver it, that starts triggering a chain of actions. So you go to the next step, you go to the next step. The issue is you can end up locking in the destructor. And that's probably a problem. That's generally frowned upon. Another option is to throw, but that's even more frowned upon in modern code. So we went with this last option, which is just panic. If you destroy your completion promise without setting a value, we panic, we core the product. The idea is we want to catch these in-house as fast as possible. It's actually turned out to be a great solution. So another option, another edge case is this disable function that I kind of told you about earlier. So if you think of this diagram on the left as a series of steps, so you're trying to accomplish, your program is trying to accomplish tasks A through H, and it has this dependency order. So you start off with H, and then you chain B, and then you chain C to that, and E to depend on both B and C, et cetera, and so on down the chain. So the question is, what should happen if you disable F? Or sorry, if you disable H, what should happen? So H is kind of at the bottom of the chain, and maybe the user canceled their request for their data reads, so we no longer care about it. It's okay for us to cancel F if and only if F has no side effects. But it turns out it's really hard to know if F has side effects. C++ lacks the introspection that you'd need, and really, even if it did have it, you probably wouldn't care about if it had side effects or not. So we allow for an opt-in solution for this problem. I'll cover that in the kind of next slide. So another thing that you could do is you could disable C. So if you disable C, what should happen to D, E, and F? Well, our solution to that is to only allow disabling for leafs. So if you say disable C, we mark it as, yes, you no longer care about C. If it had a side effect, you don't care about it anymore. Whatever, no big deal. So maybe if you go back and you cancel E, D, F, G, and H, yeah, you'll eventually cancel C, but frankly, that's a really, really unlikely scenario. So the real question is disabling even useful? I'm not sure. Maybe this low-level construct of completions shouldn't really deal with any more than a basic disabling construct. So maybe if we want disabling, we should use something else like a flow graph. So the way we deal with you picking up the kind of if your function has side effects is we have these continuation traits, which really hack the idea of is pure on top of some function. And we have this little thing where you can say pure func, and it wraps it in a structure that thus figures out, hey, this thing has no side effects. So you're explicitly picking up, yes, this is a thing with no side effects. Maybe in the future we could pick up pure function automatically. There's absolutely no way to do that in GCC right now, but, well, that I know of. So but maybe we could. And that is it. Sweet. Any questions?
So some of your optimizations are really intriguing. Have you proposed any of this stuff to the standards committee?
No, I lack the appropriate standardees to do so. It would be really helpful if somebody who was like well versed in that could maybe help me, because this is something that we found is like really handy and like really powerful for us, but I don't know how to push that forward.
So I can help you with that. The first step is to have a paper that describes the problem that you're solving, the solution, why you think that solution is good, and it doesn't need to have the standardese in it at all. The first paper is, this is a problem we can and should solve, and once you get to that, people will be available to help you do the standardese. So, do the first paper, that's on your own, and then people will be available to help you with the rest of it.
Cool.
Actually, this looks a lot like the completion token from ASIO that is actually proposed as part of the executor proposal. So why do you think this one would be useful in addition to the completion token?
Yeah, so I actually stole some ideas from completion token. That's why it kind of looks like that. Yeah, the problem that I kind of had with the ASIO completion token is it, and maybe this is just a lack of understanding on my part, is it seemed to only work in the context of an entire ASIO thing. And I couldn't really extract it out. Okay, I mean, that was kind of I couldn't figure out how to rip it out and just have it work on its own sort of...
I think that might be true for Boost ASIO, but not for the executor proposal that we currently have.
Yeah, so in Boost ASIO, the problem is, so all of this, I'd say completions were kind of made, we started them in like 2010, so there was no extra thing. It was just kind of like a thing we threw together and we're like, this helps a lot.
Yeah. And the second thing is, well, you said never use get or wait. Well, of course I disagree with that one. And if you don't want to use get or wait, just don't use future.
Sure. Well, I mean, we kind of, I don't know, went around that. But yeah, I guess it should have said never use these with a little asterisk. It can be helpful sometimes.
Well, the point is, future is not really for this asynchronous I/O thing. And I completely agree that future is not made for that, and it doesn't work very well for that. But for other things, it's pretty useful, and then it's actually useful to have the get that is blocking, and you just use the get. And the third question I have is, in one of your slides, I actually saw a std function.
Yes.
Why do you use that? Because that uses memory allocation and is pretty expensive. Probably more expensive than any mutex or something like that. So why are you using that one?
Yeah, so the reason why that is used is because I wanted to shorten it for this slide. Yeah. Yeah, you'll see it around, but yeah, I wanted to shorten it for the slides. In reality, the clever implementer will do something way better than this. There's all sorts of stuff that are just like, you would never, like a value and a callback can never exist at the same time, so why should they have separate space? Just stuff like that.
You were talking about the onComplete, which is kind of like a throwaway value. You start some thread which does some things, and then it just goes into thin air. Though, where do you store this completion object, which contains all the data?
Yeah. So G and H are kind of, in this case, where you would use onComplete. So, they're the last step in the chain. There's nobody who will depend on these values. And when I'm, say, composing something, I happen to know that I no longer care about any of these values anymore. So G and H, basically, those are the use cases for them. So, to actually answer your question, they are stored as part of the callbacks to basically E, D, and F. So since you've said this is my next step, onComplete knows, it's easier to point at F as an example here. When I say F, onComplete, part of binding that onComplete is creating this callback to kind of finish kind of the next passing of data. So it's basically just shared pointers.
So to use this, we have to store either A, B, C, E, D, or F somewhere and just keep it in our program forever?
No. Typically, by the time they're executed, so imagine you're along the chain and you're executing B right now. Well, because B is being executed right now, it's kind of pinned in memory, so it has eventually references for everything down the chain. So you don't actually have to deal with any, like explicit storing. It'll just kind of work.
You mentioned that this looks like Boost ASIO completion tokens, which I've never experienced or heard of. So I was wondering, are there other precedents or similar things out there that you think are similar to this, other than obviously like Future and the concurrency TS's stuff? Or are there other influences that we should look at to understand this better?
I mean, I'd say look at a lot of the ideas for this are in other concurrency TS proposals. The ASIO it's basically a blend of ASIO and Future. The ASIO token and that, and then some things I stole from Erlang as well. All right, I am on time. Cool, thanks.